Good morning, everyone. I am B.Shrinath from Structural Engineering Department, and my roll number is 22MST1002. And this is my digital assignment 1 for Prestressed concrete design. Moving on to my topic. My topic is deflection of prestressed concrete members. I'm going to be discussing about this of the deflection that is happening in prestressed concrete members. So, these are the topics to be covered. I will be covering where factors influencing deflections, short-term deflections, and effect of tendon profile on deflections, and deflection due to self-weight and imposed load, and then prediction of long-time deflections, and then deflection of cracked members, and then the various codes of practice that is given by IS codes. Now, here you see why control on deflections is required. It is a general practice according to various national codes that structural concrete members should be designed to have adequate stiffness to limit deflections, which may adversely affect the strength or serviceability of the structure at working loads. And that's why it requires a proper knowledge to be when the deflection forms an important criterion and for the safety of the structures. And the control on deflection is essential because excessive sagging of principal structural members is not only unsightly, but at times also renders the floor unsuitable for the intended use. Large deflections under the dynamic effects and under the influence of variable loads may cause discomfort to the users. Excessive deflections are likely to cause damage to finishes, partitions, and associated structures. Factors influencing the deflections. The factors that are like imposed load, self-weight, magnitude of the pre-stressing force, cable profile, second moment of inertia, modulus of elasticity of concrete, shrinkage and creep effect, span of the member, then the fixity conditions. Now, okay. Now we will see the computation of deflections. Computation of deflection comes in two stages. That is, so one is pre-cracking and one is post-cracking. And the pre-cracking is done using the gross MI, that is gross moment of inertia. And then post-cracking is done by using the effective moment of inertia. In both the cases, the effect of creep and shrinkage of concrete is to be increased. And we'll see more about that in the coming slides. Now, the short-term deflections of uncracked members. Short-term deflections are generally governed by the bending moment distribution along the span and the flexural rigidity of the members. The method that we use to find this short-term deflection is the Morse moment area theorem. There are actually two theorems for this. This is readily applicable for the estimation of deflections due to pre-stressing force and then self-weight and the imposed loads. By theorem 1, we get that YB is equal to integration of A to B M by EI into X into dx. This is extended from another. We got this from the moment area under the M by EI diagram between the points from A to B, and we'll go to the next theorem. In this theorem 1, it is said like the slope of the elastic curve is equal to the area of BMD by flexural rigidity, and the theorem 2 states that deflection at the center of any symmetrical or like a simply supported beam, for example, moment of area of the BND by flexural rigidity. That's what the theorem states. Going to the next one, effect of tendon profile on deflections. In most of the cases of pre-stressed beam, tendons are located with the eccentricities towards the soffit of the beam to counteract the sagging between bending moments due to transverse loads. Consequently, the concrete beams deflect upwards, that is cambering, on the application of transfer of pre-stress. Since the bending moment at every section is the product of the pre-stressing force and eccentricity, the tendon profile itself will represent the shape of BMD. The method of computing deflections of beam with different cable profiles is outlined in the following sections that we will see in the following. This is the straight tendon. For a straight tendon with an E value, we get a deflection as PE L by 2 into L by 4, the whole upon EI. That is PE L squared by 8 EI, which is a negative because it's moving upwards. And then for trapezoidal tendons, the deflection is as follows: minus of PE by 6 EI into 2 L1 squared plus 6 L1 L2 and plus 3 L2 squared. Then now parabolic tendons, for this the deflection value is minus of 5 into PEL squared by 40 DI. And for the eccentric, while the parabolic same eccentric anchors now, PL squared by 40 DI minus into minus 5E plus E2. For sloping tendon, it is PL squared by 24 EI into minus 2 E1 plus E2. Parabolic and straight tendons, when it is kept like this now, then minus PE by EI, the whole into 5 L1 squared plus 12 L1 L2 plus 6 L2 squared. and then parabolic centron with a eccentric anchorsness a into minus p into e1 plus e2 by ei, the whole into 5 L1 squared plus 12 L2 L1 plus 6 L2 squared plus PE square E2 into L squared by 80I. Now you see the deflection due to self-weight and imposed loads. During the transfer of pre-stresses, the beam hogs up due to the effect of pre-stressing. At this stage, the self-weight of the beam induces downward deflections, which further increase the effect of imposed loads on the beams. So the downward deflection is as computed like this: 5 into G plus Q into WS power 4 by 384 EI, where G is the self-weight of the beam per meter, and then the Q is the imposed load per meter. That is the uniformly distributed that is given. That we calculate. And now estimation of long-time deflections. The deformation of pre-stressed members change with time as a result of creep and shrinkage of concrete and a relaxation of stress in steel. Deflection of pre-stressed members can be computed relative to a given datum if the magnitude and longitudinal distribution of curvatures for a beam span are known for that instant based on load history, which induces the pre-stressing forces and the live loads. The pre-stressed concrete member develops deformations under the influence of two usually opposing effects, which are the pre-stress and the transverse loads. The net curvature, that is phi t at a section at any given stage, is obtained. The phi t is equal to phi mt plus phi pt, where the phi mt is the change of curvature caused by the transverse load, and phi pt is the change of curvature caused by the pre-stress. Under the section, the sustained transverse load, the compressive stress distribution is in the concrete changes with the time. However, in practical cases, the change of stress is being small. It may assume that the concrete creeps under the constant stress. Since it is doing like that, the creep strain due to transverse load is directly computed as a function of creep coefficient, so that the change of curvature can be estimated by the expression where phi mt is equal to 1 plus phi into the phi I, where phi is the creep coefficient and phi I is the initial curvature immediately after the application of transverse loads. The change of curvature due to sustained pre-stress upon the cumulative effects of creep, the shrinkage of concrete and relaxation of stress in steel. Several methods have been proposed to evaluate the curvature and simplified assumptions. The important ones are attributed to Boseman, Henry Douglery, and Corey and Susan and C. According to Neville and the ACA committee report, the creep curvature due to pre-stress is obtained on the simplified assumption that creep is induced by the average pre-stress acting over the given time using this approach, where PA is the initial stress and the initial pre-stress, and PT is the pre-stress at a time t. The loss of pre-stress is calculated by LP is equal to PI minus PT, and if E is the eccentricity and EA is the flexural rigidity, the curvature due to pre-stressing force after time t can be expressed in a way like in the way like phi PT is equal to minus PI E by EI into 1 minus LP by PI plus into open bracket 1 minus LP by 2P into 5. So moving on to the next one. A much simplified but an approximate suggestion by Lin for computing the long-time deflections is like AF is equal to AIL into A minus AIP into PT minus by PT, the whole into 1 plus 5. The principle of reduced modulus involving the creep coefficient is used to amplify the initial reflections. So this is it. And in this method, the initial deflection due to pre-stress and the transverse load is modified to account for the loss of pre-stress, which intends to decrease the deflection, and the creep effect, which tends to increase the deflection. Now, we see the requirement of IS codes as per IS 1340/1980. The final deflection, including effects of temperature, creep, shrinkage, should not exceed span by 250. The deflection, including effects of temperature, creep, and shrinkage occurring after the erection of partition, the application of finishes should not exceed the span or 20 mm, whichever is less. If the finishes are to be applied to be pre-stressed concrete members, the total upward deflection should not exceed span by 300, unless the uniformity of camber between two adjacent units can be assured. Now we see some of the problems that is on the deflection. So we can see this problem. In this problem, it is the beam cross section is 150 mm wide and 300 mm deep, simply supported over a span of 8 meter, and is pre-stressed by a means of symmetric parabolic cable at the distance of 75 mm from the bottom of beam and at a midspan, and 125 mm from the top of the beam. The force is 350 kN, and the model of elasticity is 38 kN per mm squared. We need to calculate the deflection at midspan, when the beam is supporting its own weight, and then the concentrated load which must be applied at the midspan to restore it. Now these are the given things, and then the deflection due to pre-stressing force. We saw the formula over there: PL squared by 40 Ti into minus 5 E1 and plus E2. Substituting the values, we are getting 12.74 mm, which acts upwards. So now the self weight, which should be acting downwards, where G is equal to 0.15 into 0.30 into 24 into, which is equal to 1.08 kN per meter. So the downward deflection can be calculated using the formula 5 into E plus G into the L power 4 by 384 EI, which we get 4.5 mm, which is acting downwards. So the deflection due to the pre-stress and self weight is we should add, where the previous one value will be negative. So minus 12.7 plus 4.5 is the binary minus 8.2. Now, if concentrated loads required for the second one, for the part second, of the concentrated loads required at the center of span on the QL cube by 40 DA, which is equal to 8.2 mm, because that is the deflection we got. And now, rearranging the formula, we get Q is equal to 9.9 kilonewton. So that is the load required at the center of span. So moving on to the second question, a simply supported beam with a uniform cross section spanning over 6 meters is post tension by two cables, both of which have an eccentricity of 100 mm below the centroid of the section at the midspan. The first cable is parabolic and is anchored to the eccentricity of 100 mm above the centroid at each end, and the second cable is straight and parallel to the line joining the supports. The cross section is 100 mm squared, and then the initial stress is 1200 Newton per mm square, and the other concrete section is 20,000 mm square, and then radius of variation is 120 mm. The beam supports two concentrated load of 20 kN each at the third points of the span. The modulus of elasticity is 30 kN per mm square. So we should use, and they're asking us to do this in a Linz simplified method, and the creep coefficient as 2. So now we'll see the instantaneous deflection of the span, and then the deflection at the center after 2 years, assuming 20% of loss in prestress, and the effective modulus of elasticity will be 1/3 of the short-term modulus of elasticity. So the given details are wrote at the first, and then now the downward deflection due to self weight is as per the formula W5 into E plus G into W square L power 4 by 384 EI. We get the answer as 0.7 mm, which acting downwards, and the downward deflection due to the concentrated loads is 23 QL cube by 684 EI, where we get 14.1 mm, which is acting upwards. So the deflection due to parabolic cable is PL squared by 40 DA into minus 5 E1 plus E2, which we see in the previous slides. The answer is 3.29 mm, which is acting upwards. And then deflection due to pre-stressing of straight cable is minus PE L squared by 80A, which is equal to 4.92, which is acting upwards. So the instantaneous deflection due to pre-stress plus dead load plus live load is as follows. And then the 6.65 mm, which is acting downwards. And for the B, at the end of 2 years, where EC will become 1/3, and then the loss of pre-stress is 20%. The upward deflection is as follows, which is 19.65 mm, and then the downward deflection is 44.52. The net deflection is so we're subtracting those two, and we're getting 24.87. So now, in this question, we'll be finding the pre-stress concrete having a cross section of 5 into 10 power 4 mm square, and then it's simply supported over a span of 10 meters and has a UDL of 3 kN per meter. And the tendons follows a trapezoidal profile. It is having trapezoidal profile with the eccentricity of 100 mm within the middle third of the span, and then the AP is equal to 350 mm square, having a effective pre-stress of 1290 Newton per mm square. We need to find the short-term deflection and long-term deflection, and the given values are given here. Assumed values are given here. So now we find the deflection due to pre-stressing force, that is AP into the formula, and then substituting the values, we get to minus 31 mm, which is acting upwards, and then the deflection due to non-permanent load is 12Q L power 4 by 384 EA. While substituting, we are getting 12.8, which is acting downwards, and then the deflection due to permanent load is that is sustained load. We get 5G L power 4 by 384 EA. It is acting downwards and 22.8. The short-term deflection is we should add the 1 to 3, that is the non-permanent load, where we get the answer as 4.6, that is acting downwards, and then the non-permanent load which is not acting is AS minus 31 plus 22.8, where we get the answer as minus 8.2, which is acting upwards. And then the long-term deflection is as follows, where the FC we need to calculate 451.5 into 1000 by 5 E power 4, and we get plus the value, we get 19 Newton per meter mm square, and then the loss due to relaxation is 10%, so we are giving that, and then loss due to shrinkage is as follows, which is 19 Newton per mm square, and then loss due to creep 23 Newton per mm square, so that's 442. Pre-stressing forces 442 350, so 154,700 Newton. While the final pre-stressing forces, the subtract this 551.5 minus 154.7, where we get 296.8 kilonewton. So the average forces as follows, and then 374.15. So the long-term deflection is the 1 minus the deflection due to loss of pre-stress, and plus the deflection due to average pre-stressing force due to the creep with phi equal to 2. So applying this in the formula, and then we get 72 mm, which is acting upwards, and the short-term deflection due to permanent load is 1 plus 5 into short-term deflection. Applying the formula, and we get 68.4 mm, which is acting downwards, and then the long-term deflection due to non-permanent load is 12.8, which is acting downwards. So total long-term deflection is, when non-permanent load is acting, which is 4, 5, 6, we get 9.2, which is acting downwards, and the non-permanent load is not acting is minus 4 plus 5, which is minus 3.6, which is acting upwards. So thank you, sir. Thank you for listening. And I'm B.Shrinath-22MST1002. Thank you, sir.